just go back to that example and divide out the charge?
No,
Not for
because
this, for your electric field or electric potential in an atom.
yes, you basically just look at how the proton in the nucleus affects the space around it, and you basically divide out the electric electron. But it ends up being a relatively simple calculation. Getting to the energy then becomes a simple calculation without having to necessarily do the 1/2 MBs blah 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 squared and stuff. Yeah, the technical term. Sorry, but I fall into my Harvard accent every once in a while. Okay, so let's take an example where we have a value of minus Q and plus Q at a distance away, a point out here, P, and this distance here, 0.3. This distance here is 0.03. Oh, we've seen this one before. Now, to calculate E directly, you probably wouldn't want to use a dipole relationship for two reasons. One is it assumes that the distance between these 2 points is negligible. But it isn't negligible. The difference between 0.3 and 0.31 is not negligible when you're taking a cube. Right? When you use the dipole calculation, you're using a 1 over r or z cubed relationship. So you don't want to do that anyway because they're not that indistinguishable. Now, easiest way to approach it, potentials are scalars. They add and subtract as numbers. So, I guess I called this Q1 and Q2. I'll leave it numerical. So one is a positive, one's a negative. It's Q1 and Q2. The potential out here then, and this is why it's so helpful. VP is just the potential due to Q1 plus the potential due to Q2. And they're point charges. So the calculation doesn't get any simpler than that. As equations go, we have R1 and R squared R2. So we have two vectors for position, distance separation, with their respective charge. So if I were going to calculate the potential, I would start by saying, well, Q1, and it's going to have a positive or a negative value, certainly, divided by 4 pi epsilon naught R1, it's just that, plus Q2 over 4 pi epsilon naught R2. And we can identify that these are separation values. These are not absolute distances, right? Because for any particular charge, you have a radial symmetry. Wherever you are around it, it isn't going to change its value positive or negative based on the fact that you're on one side or the other of the charge. So these are basically magnitude values. So the distance of separation R1 then would be this squared plus this squared, take the square root. And the separation distance for R2 I've got the, actually, 3.3 meters. Or if you will, to simplify it, at this point you're probably plugging numbers into a calculator. Oh, it's the same Q, isn't it? So we can just bring out the magnitude of Q. And I'll deal with that. And this is a negative. And this is a positive. So Q is the magnitude of Q1, the magnitude of Q2, and I put my minus sign here. So I just left the sign in, because you still need the sign, but I just left it in there like that. So it becomes, in this case, a simple calculation. So if Q then was what did I use? 3 microcoulombs negative. And Q2 was plus 3 microcoulombs. By the way, a micro is 10 to the negative 6th. If you didn't know that, it'd be worth the chance to just ask. Right? What's a micro? Rather than forget to use the units. A couple of you just didn't put the units in and just left it as a number. You get some calculation, you're off by 1,000,000, by 6 orders of magnitude. Now those are just, easily correctable things, but, right, details are the difference between bridges, standing, and falling. So, reasonably simple calculation, you tell me what the number is.
And then our equation changes at the end now, because we have two different, oh, it's the same.
Yeah, so I gave the same values, and I did give basically dipole values, but I didn't intend for you to do it as a dipole problem. So we basically have 3 times 10 to the negative 6 divided by 4 pi times 8.85 times 10 to the negative 12 Coulomb squared Newton meters squared, or 9 times 10 to the 9th times this. This is 27 times 10 to the 3rd. Right? When in doubt, write it out in terms of Coulomb's law, if you can. So we have 1 over...
Should be 0.3, isn't it?
This is like 0.31 or
0.301.
Yeah,
0.301. Keep the 01. They're close enough that you can almost get away with it, but keep it for now. I know that the significant figures now go to hell in a handbasket. I recognize that. But, it is pretty close to 0. However, the reason why I want you to not necessarily just completely throw that out is when you calculate the electric field, there's like 3 orders of magnitude difference between the x and the y components, certainly, because they cancel out in the x direction. And the y direction is relatively small. But it's still a finite number. It's still a measurable, calculatable number, even though it's relatively close to 0 in a significant figure sense. You can always round later. It is going to be pretty close to 0 in this case. It's,
I got 300.
Unless I plug this thing into my calculator incorrectly, because I've got 446.
Yeah, I got somewhere.
okay, so it's not quite 0, is it now? Using the 0.301?
Yeah, well,
Mhm.
I just used a number that was in my calculator, it's like 10 sig figs, so.
Yeah, I used the 301, I got 298. So.
You know, it's rounded later, but it makes a difference. You keep the numbers in your calculation because it would in fact be pretty close to the difference between 0 and whatever that number is. Okay, so I don't know what the number is. Do you have a value for it? It's about 400 though?
Yeah.
Positive, right?
Yeah, probably.
It's joules per coulomb. It is in fact a volt, but I don't joules per coulomb.
Yeah.
So is that, I'm going to put a plus here against 3. Now we would expect it to be positive if for no other reason. It's slightly close to here. There. Now, that's where it gets fun. Woo! Woo! What? We're doing physics, exactly. Everybody knows physics is for the bird. And that has a different meaning than otherwise we would have thought before. You don't believe me? When in doubt, ask the colonel.
Physics is gonna say that we've had a bird in
0.
the lab.
It's my physics.
By the way, I mentioned that to several colleagues and superiors, and everybody was cool with it. It was like, oh, that's really cool. You should call me in. Like my boss said, oh, I'd love to have seen the bird.
Oh, okay. Yeah.
So, you know, I was afraid I was going to take hell for it, but
Cool.
It was cool.
it was all good. All
It
good.
was all good.
Okay, so how might we calculate the electric field at that point, right? Because that was where it was sort of a 50-50 venture. Either it was a straightforward, easy problem, maybe a little bit of math error in there, positive, negative, or it was completely sideways. The question is which. How would we do it? Okay, so what might we need to do? Let's begin there.
So we need to take this derivative.
Not yet. Our r's are not pointing in, are not referenced to the same values. So the first thing we need to do is to establish a coordinate system. Now, when you establish a coordinate system, in this case, it's not always helpful to pick a point charge. It might be, but if you pick a point charge, understand one thing. You aren't going to switch to the other point charge when looking at the other electric field or the other voltage. Okay? So anytime you're dealing with vectors and you're combining multiple quantities, you've got to pick a single solitary coordinate system. So maybe to make life easier, you call maybe Q2, Q1, 0, maybe Q1 or Q2 just because it's flat for this. So, start there. So let's assign a coordinate system. On Q2. And the x and the y make absolutely no difference to me. But what do the two fields look like? What will they look like? This is where I got a little bit disappointed with a couple of the exam solutions. Is that calculations without a context are a perilous, perilous journey. It doesn't hurt to know kind of how things in a ballpark ought to relate. Is that reasonable? What does the electric field look like for Q1? Q1's negative, so it's pointing towards.
Right.
So there's Q1, or there's E1. No value, but there's E1. What about E2 or E for Q2?
It's
Not in, it's positive charge. It's away. and it's ever so slightly larger than this. Maybe not much, but ever so slightly in size.
It's something like 0.1% larger.
Well, we haven't calculated it yet, so let's just leave it in this form. Well, what does this tell us, first of all? It tells us that this component will be subtracted with the x component of E1. And I'm running out of colors here for this wow. So we can think of E1 as having a horizontal component this way and a vertical component this way. Reasonable? Because these are subtractive, chances are it's going to be a smaller value than this one, just by inspection. So, as we lay it out, maybe with respect to here, got to pick a point where that's reasonable for your coordinate system. We have to express what the potential is in x and y relative to this origin. So what would that look like? What would the potential, so now maybe, I don't know what a reasonable coordinate system is, but maybe we call that direction y. And we can be traditional Cartesian, or we can just maybe even say that's the y or x direction. The only advantage to that is that it's positive. And the x component will be positive along this way, and the y component is positive upward.
Why would you want to repeat it?
Right.
Oh, there's no reason not to. It doesn't matter which direction we go. If we call this the origin, then the electric field, well, I guess you could still point it in this direction. It'd just be negative. But our electric field now will be a function of this being 0, so it's going to vary on both sides in kind of a screwier way than it would using this position. Just think about Q1, or Q2, I mean. If we looked at E for Q2, and we call the origin P, then the electric field would look something like this. Right? When you're at 0, you're out here. And so you're going to have these weird offsets in X and Y. Mathematically, it's absolutely possible that by having this weird reference, it could cause a certain amount of potential angst. So, there's Q2. So we're out here somewhere at point P. How would we express the potential in terms of X and Y? Yeah. I'll leave out Z. V2 is easy right there. I call this the positive direction, so V2 would be Q over 4 pi epsilon naught. And because I call this direction the X direction, that's why I got it. Rather than, if this were 0, it would be negative, it would be 0 here. Minus this distance. So it'd be some, it would just be here backwards to try to keep track of the coordinate system. Now, what would then V1 look like? That's because that becomes the challenge now. How can we determine V1? It doesn't have components. what's gonna be a Q 4 pi epsilon naught of minus Q. And then the question is, what's the rest of it? Separation distance. How do we express that separation distance in terms of x and y?
X squared plus y squared.
Now, let's see if that's potentially, hard to find again, potentially consistent. If we approach it this way, then when x is 0 and y is 0, that would imply that potential is infinity here, right, as you get on Q2. But it needs to be up here. It needs to be infinite here and decrease with respect to here, not to here. When you're at the origin, what's the voltage at the origin? Let me say it that way. What would be the potential due to Q1 at Q2? Because you still have this distance of separation. This didn't exist, but you're still this far away. What's the separation distance here? What's the value?
0.03 meters.
0.03 meters, but if you use x and y, you got a problem. What's the problem? Or I mean, if you call this your 0, 0 origin.
0.03 meters minus x.
So we have to adjust this somehow. The x works fine. But in the y direction, we have to account for 0, right? So it's going to be, would it be y minus that 0.3?
0.03 squared, right? Y squared.
Yes, the whole thing. Or maybe we could call this y naught or y prime if you wanted to keep it in a symbol form. Let's do that.
Yeah.
Let's call this y1. Just, the only reason I'm doing that, y1 is 0.3, but let's just keep it in some.
Yeah.
All I'm doing is trying to get a coordinate system that when my potential is 0, it's a reasonable number. When I'm out here at y equals 0, I've still got y1 squared plus x squared square root. So this is still consistent out there. So I just gotta slide my x-axis, my y-axis over for that. Okay. So what's my total potential? Because I need to do that before I take the derivative, right?
It's the sum of the two.
Just the sum of the two, but it's going to be an equation form now, because you got to take a derivative of the sum. Okay? Therein is the problem. So v at point P, then, or I should say v as a function of x and y. Got to make sure I'm keeping it general. Would correspond to q over 4 pi epsilon naught, positive x direction, And let's double check something here. There is a positive,
That should be
and,
negative, right?
pardon me?
So that one under X should be negative,
It's positive because I called the X direction forward.
oh,
Only, and I just did that so we can keep the magnitude that way straight. So when in doubt, keep the coordinates. If I were on the other side, I'd do it the other way. Or if I were looking in all space, I'd do it the other way. In fact, I'd probably use spherical coordinate system if I wanted to look all over me here. Simplify what would make more sense. Play with it in different ways. So it would be a positive X. And then we would have, because of the minus q, minus 1 over the square root of x squared plus y minus y1 squared. So that would be my function.
Maybe we can put this into a simpler form before we have to take the derivative.
Probably not a bad idea.
We don't have to have so many composite functions there.
So at least put it in, well, first of all, we could probably take a common denominator. For taking a derivative, it might be helpful. Probably. It's not, in the end, it should work out the same. But let's take our break now. Let's come back and let's have you guys see if you can solve this out this way. And we'll compare it to the original. That'll be directly from 2 o'clock.
Definitely.